I'm going to talk about data cleaning and how we are doing that with Hadoop. It's going to be only a little bit machine learning, and I will try to do that as simple as possible. Shortly, I'm going to introduce me and myself and company. Then I'm going to point out why data cleaning is important for us. And then most of the time I will spend in presenting the algorithm. And hopefully I will reserve a few minutes for the questions. Well, in the past I was always giving the talks about how we combine Lucene and Hadoop to do reporting. And some of the people told me, okay, you are abusing Lucene and so on, but then as time came, we saw that you have doc values. There are some other search products that have reporting and aggregations and so on. Currently, we are experimenting with HBase, and I have some background in HBase. And most importantly, I have PhD in machine learning area. And in this talk, I'm going to show you that it's not so scary, that you can solve very difficult problems very easily. What about the Zanox? Zanox is an affiliate marketing company that brings together publishers and advertisers. What about publishers and advertisers? Advertisers on one side are online shops, for example, and they need traffic, they need visitors that are going to buy stuff. And on another side, publishers, something like blog sites, they have visitors because they have useful content and they want to monetize that content. How the Zanox comes between, Zanox is bringing them together, and for Zanox it's important to point out that it is a performance-based network. What does it mean? The traffic that publishers are via Zanox sending to advertisers are going to pay commission only in the case that they earn money. That means only in the case that a particular visitor bought something. And then Zanox is going to get a fee, and also the publisher is going to be paid. And let's say that I shortly introduce the Zanox, and I will put the Zanox in a footnote together with the Lucidworks. Let's start about example that is illustrating why data clean is important. Well, advertisers have the so-called product offers. Product offers are products that they are selling, and they are sending product offers to Zanox. And it's not only that we have only one advertiser, we have thousands of them, like 10,000 of them. And they're all sending product offers. Not all, most of them are sending product offers. That means you can imagine how many product offers we have. I will give some numbers at the end. And on the other side, you have publishers. Zanox provides the search API, and publishers are using that to build some interesting products. That means publishers are going typically to send the queries, like in this one, and point out that some of the queries are requesting also for facets. About the number of queries, it depends, but it's, let's say, 20 to 50 per second. And the queries that are sent are used by publishers on different ways. Those are the numbers that I promised. And about the numbers, it's important to point to see that we have between 2 to 5 million product offers sent on a daily basis, that in a database, in a collection, we have more than 100 million products. And can you imagine how the products look like, product offers look like when they're sent from so many different sites? Not to point out that some of the advertisers try to manipulate in the sense that maybe they know that we are using Solar, and then they try to boost some terms or so on. But in this talk, I will show what is happening, for example, when you are doing facets. And if you have a nice clean collection, then everything looks like on the left side, and in reality, you will get something on the right side. And the right side is a more or less broken user experience. That means we have to somehow normalize the data. We have to bring, in this case, the same manufacturers together. And that's also important not only for faceting, also the result grouping or field collapsing benefits from that. And you will have more accurate term frequencies, and also your filtering is going to be more efficient. And let's see how we are doing that. Well, the most important part, and because I was scared that I won't have enough time, it's clustering, and I'm putting that on the beginning. And if you got the idea from the clustering, the rest of the presentation is more or less not so important. The idea in clustering is we used clustering to transform one quadratic time consolidation algorithm into linear one and make it usable. In the second block, I'm going to briefly talk about how we are comparing different attribute values. That means which functions exist, shortly present them, and see how we can combine them. Actually, how we can learn what is the best way to compare values. And let's start with the clustering. Well, initially, let's say that I have only 5 values. And what I have to do, if I don't use clustering, I have probably to compare exhaustively each value with all others in order to figure out that in this case, V1 and V4 are the same, and V2 and V5 are also probably the same. But that's quadratic complexity. And if you think that your number of different values is something like 1 million, and trust me, when I'm talking about manufacturers, for example, because thousands of advertisers are sending the data, we will have like more than 1 million different manufacturers. And exhaustively comparing all of them, it doesn't work. And what we are doing clustering. Idea with the clustering is to somehow put the values that are potentially similar in the same cluster. Cluster is going to be much smaller, and because it's much smaller, there inside the cluster, I can exhaustively compare all the values. In that sense, we are using the Solar tokenizer and filter factories, because that's something that I believe Solar is very good at. We start with a white space tokenizer that is preserving all alphanumeric characters, because as a second step, we are going to use word delimiter filter factory that is going to cut the values further in pieces. And those examples that I'm giving are some of the typical tokens that are occurring in our case, and after being pushed through the word delimiter factory, they are transformed as shown. And finally, very important step is removing the stop words. Stop words here are the words that are domain-based, and more or less, I don't like stop words because stop words are going, as it will be soon clear, create very big clusters. And very big cluster means, okay, inside the cluster, I have to compare exhaustively, and that is really costly then. Here I'm giving some examples of the stop words. That means I don't like to see the following words. And finally, here is the very important part. Believe or not, there are spelling errors also. And we want to be able to detect that different values, even when there are spelling errors, are the same. And I want to be quite relaxed when I'm clustering the values. That means, if I'm not sure for the value, for example, V1 and V2 or something like that, let's put them in the same cluster. Or let's do so-called fuzzy clustering, where I'm going to put the value in multiple clusters. What I have in the last step is a sound excoding filter. It's going from each preserved word to create the sound excodes. And those sound excodes, okay, here is what sound X filter factory does. For each sound excode, I'm going to create one cluster. And the fuzzy clustering means I'm going to put the value in the right clusters. That means when I have, when I split that value on several tokens and they survived all those transformations on the way, I will put that value, let's say, in 2 clusters. Here is the short summary of what I mentioned. And what I'm doing right now with the clusters. Well, the point out with the clusters, they are much smaller. Okay, in this example, what the heck I have, I had 5 values, and from 5 values I create 3 clusters, but each cluster has the size at most 3. And each cluster can be independently processed. And there is the part where we use Hadoop. That means for each cluster, I'm going to create one map task. And inside a map task, I'm going exhaustively to compare all the values. Here it becomes important why I remove the stop word. I don't like the cluster where I'm putting the values together only because they have the token corporation, for example. That cluster is going to be huge. And because I have the stop words removed, and those are the words that are too frequent, more or less I'm controlling the size of the cluster. And by controlling the size of the cluster, I'm making sure that I can process each cluster in a constant time. It sounds silly in this case, but when you think that you have 1 million different values, and if you can guarantee that I can process the cluster in a constant time, and if I know that I have at most linear number of clusters, because I'm also I can also bound the number of tokens in each value, I have a linear time running algorithm. And at the end of the presentation, I will show some concrete numbers. The difference is huge. It's unbelievable, and the difference between quadratic time running algorithm and linear one, when I have as an input 1 million different values. What is happening with the map task? They are comparing the values, and the values that are similar enough are going to be propagated. The values that are not similar enough are going to be removed. And here I'm illustrating what the Hadoop framework is doing for you. Hadoop framework is sorting automatically on a key. That means in a reduce task, you are going to get all the value, all the key value pairs sorted based on the key. And why is that important? Well, we will see that, okay, here what reduce task does is checking, is consolidating. For example, if I have 2 possible transformations for the same key, is going to check which one has the higher similarity rate or better confidence. And the sorting part is important because I'm going to put the results in one FST. And the Lucene library for building FSTs says your keys have to be sorted. And that's something that you are natively getting out of the Hadoop framework, that is sorting the keys that map tasks are producing before sending to the reducer. More or less, again, the summary. I'm going not to repeat myself because we lost some time on the beginning. And that's the FST. And here I'm going to print one short animation about FST. And while that is doing that job, what I want to say, we have a lot of manufacturers that have very similar names and actually are different manufacturers. From the point of FST, that's very good because you can very compactly represent that. From the point of determining the similarity, that's a challenge because you will have the manufacturers, for example, that have the similar names but actually are not the same, and you don't want to introduce such transformation. About why we used FST, well, the result of that data cleaning is compactly represented as FST, and why is that important? Here is the size. I think it's a little more than 20 megabytes, 25, and it is quite built in 2 seconds. And the result, how we are using the result, for example, you can put that in update processor chain in Solar, and you want to have that as small as possible because you don't have memory to waste. It's quite okay that it's expensive to build maybe that. You have Hadoop and complicated clustering, but the result is very compact. And you can move those 25 megabytes easily and load in the memory and do on the fly during the indexing conversion and cleaning. And the most important part is done. Now, let's see. What about similarity? Well, again, that's one of the examples, and I want to see how I can compute the similarity. Well, again, I can call different Solar tokenizers and filters to help me. For example, I can use white space, word eliminator again, lowercase, and stop word in order to transform those attribute values in some sets of tokens. And those sets of tokens I can use to plug in different functions. And there are many different functions that now can be used. Here you have different functions. Many clever people invented different functions that you can use. Here I had the Jacquard index, dice index, overlapping index, and so on. Let's take the second example, and the second example is that I have the spelling error. I'm explaining the Levenshtein distance more or less that is able to determine that those two values are quite close. Here what we have that the Levenshtein distance can address those spelling errors, and what we haven't seen, unfortunately, it's able to very efficiently implement Levenshtein distance by using dynamic programming, and that's what we did. But I can have another example. Again, unfortunately, you cannot see, but believe me, he's going to compute that the distance between those two manufacturers are again very small, and that's not what we want to have. And that's what we call the false positive. That means Levenshtein distance is determining that those two values are very close, and unfortunately, it's going to say transform Cisco in Casco, and that's not what we are aiming. And what we are doing here, well, Cisco and Casco are not alone. They are part of a much bigger entity, and that much bigger entity is actually the product offer. That means every single product offer has many different attributes, and you can use those attributes to build the context. And that context can be used for figuring out that Cisco and Casco are actually different manufacturers. The attributes that can be used, the attributes that are used are, for example, name, description, category, and so on. And from there, we can identify the words that are most important, and those words can build the context for those two manufacturers. And of course, we don't have only 2 product offers, we have many of them, and you can collect the most important words for these 2 manufacturers. Okay, when you have those words, those are the sets of words, you can use, for example, Jakarta index, and unfortunately not aligned well, and we will call it semantic Jakarta index. About the distance functions that I presented, and there are much more. That means it's quite easily to find a lot of fancy formulas that you can usually quite easily implement. Sometimes like maximal common substring, it's a little more complicated to implement, but you can find libraries that implement that. And on the left side, I have the training data. That means we manually identified which manufacturers are the same, because somehow I want to learn. And learning the distance function is a big challenge. Here I will show how we can do that very, very easily. And while hopefully this moving runs smoothly, because that's what I did especially for this slide, okay, we decided to do a linear combination. Hopefully it's obvious that every distance function is actually a feature. And because in reality those distance functions are comparing the 2 particular attribute values, they are more or less maybe dependent. And when you have dependent features, some machine learning techniques can experience some difficulties, cannot converge well, or it is not converging at all, and so on. But if you do linear combination, problem becomes easier. Still, you have to be careful. The point why I intentionally put here so many distance functions is to see that you have a lot of coefficients. And the question is how I can figure out and how I can learn coefficients. We tried some fancy stuff with genetic programming, but I thought let's present what we did on the early beginning, because that was successfully used for a long time, and it was very easy to understand. And the solution that we used was a grid search. Grid search is usually applied when you are learning. What is grid search? Grid search is that you exhaustively try all combinations. Okay, we have Hadoop. We can do a little bit brute force, but more or less here you have too many coefficients to learn. And if you are taking, for example, only 10 different values for each one, here you have 10 to the power of 19, I think, and that's a huge number. And you cannot afford to do that. You are randomly initializing the coefficients. And those values that are randomly, I'm so sorry, here should not be the white box. I'm going to do again. That means I'm going to create some points. And let's say that I can afford a few random initializations. And then around each point, I will do the grid search. That means I will examine the neighborhood of that point. How I'm examining the neighborhood and how I'm creating the neighborhood is not so important, but I know that inside of the neighborhood, I can have, let's say, at most so many different combinations that I can try. And I'm examining each neighborhood as a Hadoop map task. As a result, I'm going to find a better combination of coefficients, and one is going to win. And that is winning are going to be my distance function. But my distance function, I don't like to have so many distance functions that I'm combining, because remember from the clustering part, I'm going to use that distance function exhaustively inside every map task and to I want to have distance computed as efficiently as possible. Because of that, I'm going to remove the distance functions that have the small weights. It means now it should happen that the distance functions with the small weights are disappearing, and then I have, now I have the situation with less coefficients to learn. That means my search space is going to be smaller, and when I am expanding the neighborhoods, I can cover greater part of the search space. In reality, it's not so that that grid search is giving you the idea which function is important, but you have also some kind of intuition that is helping you remove some of the distance functions that you don't need. And again, I'm doing the same, but now I have a very small search space. Again, random initialization, grid search around, and here it looks like a complete grid search. That means at the end, when you have so many coefficients, you will cover almost everything. And that's what real grid search does. Okay, in this case, we have grid search implementation based on Hadoop. And finally, let's uncover the functions. And those are actually the functions that we, at the end, finish up. That means, more or less, you have a function like Levenstein distance that is sensitive to the spelling errors. You have that semantic Jacquard index. That means the one that is taking into account the context in which you are using the terms. And you have the normal Jacquard index and also the function that is doing maximal substring overlap. And because the time is quite, I'm almost done. This point was important here. I'm executing single comparison in a time between 5 and 30 milliseconds. And here is the point. If you don't have the clustering and if you are exhaustively comparing 1 million attributes, then everything is going to take more than 100 years. But with fuzzy clustering, and at the end, when you put that in a quite small Hadoop cluster, the whole process is going to last only 1.5 hours. That means you made a dramatic improvement from 158 years to 1.5 hours. And that was more or less for me the most important lesson. I'm so sorry that you haven't seen the similarity part. But trust me, there you are simply taking different functions that already exist, trying to combine them, and at the end you are finishing with only few of them that you use and that you can execute quite efficiently in 5 to 30 milliseconds. Sorry for the slides. But it's good that we somehow managed.